Torsion. Introduction. Torsion force is a twisting force that is applied on an object by twisting one end when the other is held in position or twisted in the opposite direction. Different materials have a different way of responding to torsion. Some will deform, crack, or even break depending on the type of material. So these are the images when we applied a twisting force and will cause torsion. Torque. In solid mechanics, torsion is the twisting of an object due to an applied torque. And twisting moments or torques are forces acting through distance so as to promote rotation. And simple torque is equal to F times L, or the force times the length, and that's the simple torque. Finding the torsional shearing stress or tau for a solid or hollow circular shaft subject to a twisting moment T, the torsional shearing stress tau at a distance P or L from the center of the shaft is tau is equal to T times P all over J, and the maximum shearing stress is equal to T times R all over J, where J is the polar moment of inertia of the section and R is the outer radius. We have the radius, the torque T, and the length L, and we have an angle theta. And for solid cylindrical shaft, J, or the polar moment of inertia, is equal to pi over 32 times d exponent 4, where d is the outer diameter. And the maximum shearing stress is equal to 16t all over pi d cubed. For hollow cylindrical shaft, J, or the polar moment of inertia, is equal to pi over 32 times the diameter outer exponent 4 less diameter inner exponent 4, and the maximum shearing stress is equal to 16t d, the big diameter or outer diameter, divided by pi times the difference of d outer diameter exponent 4 minus the smaller d or the inner diameter times or exponent 4. So this is the outer diameter d, the big D, and the smaller diameter or the inner diameter. Angle of twist. The angle theta through which the bar length L will twist is theta is equal to TL all over JG, and it is in radians, where T is the torque in Newton millimeter, L is the length of shaft in millimeter, G is the shear modulus in megapascal, J is the polar moment of inertia in millimeter exponent 4, the big D and the small d are the diameter in millimeter, and R is the radius in millimeter. Power transmitted by the shaft. A shaft rotating with a constant angular velocity W in radians per second is being acted by a twisting moment T. The power transmitted by the shaft is P is equal to T times W is equal to 2 pi Tf, where T is the torque in Newton meter, F is the number of revolutions per second, and P is the power in watts. Example number 1. The steel shaft, 3 feet long and 4 inch in diameter, carries the end torque of 15 kips/foot. Determine A, the maximum shear stress in the shaft, and B, the angle of twist of the shaft. Use G, which is equal to 12 times 10 to the power 6 psi, and this is for steel. The length is 3 feet, the diameter of the shaft is 4 inch, and the torque 15 kips/foot given. So we have length L, which is 3 feet, diameter or D, which is 4 inch, torque T, which is 15 kips foot, G, which is 12 times 10 to the power 6 psi, and this is for steel. Then we find A, which is the maximum shearing stress or tau max, and B, the angle of twist or theta. Solution. A. Formula for maximum shearing stress, tau max is equal to 16t all over pi d cube, and 16 times the torque T, which is 15 kips foot, and we need to convert the feet to inch, or 12 inch is equal to 1 foot, and we need to divide pi and the diameter, which is 4 inch cube. So we compute, so 16 times 15 times 12 divide by pi, and we divide also by 4 cube, and the value is 14.32, and the unit is in KSI or kilopounds per square inch, and this is the maximum shearing stress. Next, and for B, which is theta, and the formula TL all over JG, and this is the equation for angle of twist. And what is J? J is the polar moment of inertia, and the formula for J is equal to pi over 32 d exponent 4. We substitute, so pi over 32, and when multiplied by the diameter, which is 4 inch exponent 4, and we convert it to J is equal to pi times 4 to the power 4 all over 32, and it is equal to 8 pi, and the unit is in inch exponent 4. Theta is equal to T, which is 15 kips foot, or 15 times 10 to the power cube for pounds, and we convert feet to inch, or we multiplied by 12, and multiplied by the length, which is 3 feet. So this is 3 feet, and we convert feet to inch, so 12 inch divided by 1 foot, and we divide by J, which is 8 pi, and we multiplied by the G, which is 12 times 10 to the power 6, and is psi, and we convert the angle to regions, which is 180 degrees is equal to pi. So 15 times 10 to the power cube times 12 times 3 times 12, and we'll multiply it by 180, and we divide by 8 times pi squared times 12 times 10 to the power 6, and the value for theta, it is equivalent to theta is equals to 1.231 degree. So this is the value for theta. Example number 2. The 16 feet solid steel shaft is twisted through 4 degrees. If the maximum shear stress is 8000 psi, determine the diameter D of the shaft. Use G, which is equal to 12 times 10 to the power 6 psi for steel. So we have here 16 feet long, T, and the diameter given. The length L, which is 16 feet, the angle of twist, which is 4 degrees, the shearing stress, which is 8000 psi, the shear modulus, which is equivalent to 12 times 10 to the power 6, and this is in psi. Find the diameter of the shaft. And solution. We need to convert the angle theta into radian. So we have 4 degrees, and the conversion 180 degrees is equal to pi, and it is in radian, or pi radian, and we divide by 180 degrees, and in terms of pi, 4 over 180, pi over 45 radians, and this is for theta. And the formula for angle of twist, it is equivalent to TL all over JG, while shearing stress maximum, it is equal to TR all over J. So we convert T, and it is equal to shearing stress times J all over R. So we have equation 1, equation 2, and convert to equation 3. Then theta, equation 1, we have equation 2 for T, or equation 3, which is stress times J all over R, and we multiplied by L over JG. So we convert T to stress times J all over R, and we cancel out J, and shearing stress times the length all over R, the radius, times the shear modulus, and that's for theta. And after that, we change the value for theta, which is pi over 45. Pi over 45 is equal to the shearing stress, which is 8000 psi, and we'll multiply it by the length, which is 16 feet, and convert it in inches, or 12 inch over 1 foot. Cancel out foot, and we divide by the radius, and the radius which is based on diameter, or d over 2, and we multiplied by the shearing modulus, which is 12 times 10 to the power 6, and we find the diameter, or in terms of the value, so 8,000 multiplied by 16 times 12, and convert it times 2, and multiplied by 45, cross multiply, and we divide everything by pi times 12 times 10 to the power 6, and let's see what is the value for d. So you have 8,000 times 16 times 12 times 2 times 45, and we divide by 12 times 10 to the power 6, and we divide by pi, which is 3.1416, and the value for diameter d is equivalent to 3.67, and it is in inch, so the diameter of the shaft is equivalent to 3.67 inches. Example number 3. The compound shaft consists of bronze and steel segments, both having 120 mm diameters. If the torque T causes a maximum shear stress of 100 megapascal in the bronze segment, determine the angle of rotation of the free end. Use G, which is equal to 83 gigapascal for steel, and G, which is equal to 35 gigapascal for bronze. So we have here the bronze, and the length is 4.5 meters, and for steel, which is 3.5 meters, and we have the diameter of 120 millimeter, and we need to find the torque T at the end of the shaft given. So we have diameter for both bronze and steel, which is 120 millimeter, and we convert it to meter. So we have 1 meter is equivalent to 1000 millimeter. Cancel out, and the diameter in terms of meter, it is 0.12 meter. Shearing stress, which is 100 megapascal, or in terms of Newton meter squared, or Newton per meter squared, it is 100 times 10 to the power 6 Newton per meter squared. G for bronze, it is equal to 35 gigapascal, or it is 35 times 10 to the power 9 Pascal, or Newton per meter squared. Shear modulus for steel, it is equivalent to 83 gigapascal, or 83 times 10 to the power 9 Newton per meter squared. We have the length for bronze, which is equivalent to 4.5 meters. The length for steel, which is 3.5 meters. Find. We need to find the angle of rotation of the free end. So we need to find the value theta, or the angle of twist. Solution. First, we need to find the value for T, or torque, using the maximum shearing stress. So the formula, maximum shearing stress is equal to 16T all over pi d cube, and T, we have pi shearing stress d cube all over 16. So we substitute the values pi times the shearing stress, which is 100 times 10 to the power 6, and we multiply it by the diameter in terms of meter, which is 0.12 meter cube, and we divide by 16. And the value for torque, so pi times 100 times 10 to the power 6 times 0.12 cube, value for T is equal to 33,929, and the unit is Newton meter. So we have now the value for T, and the formula for torque, it is equivalent to TL over JG. So we have two values or segment. We have the bronze and steel. So we have the same value for torque and the value for J. However, the length for the bronze and the length for steel are different. Also for the shear modulus. So we summarize T over J, and we need to sum up the value for L over G for bronze and steel. So the value for T, it is equivalent to 33,929, and we divide by what is J, and the value for J based on the formula, it is equivalent to pi d to the fourth all over 32. And if we equate pi times 0.12, which is the diameter, exponent 4, and we divide by 32. So we have J, which is equal to 3.1416 times 0.12 exponent 4, and we divide by 32, and the value is 2.04 times 10 to the power negative 5, and it is in meter to the fourth. So we have here 2.04 times 10 to the power negative 5, and the summation for bronze and steel, we have L for bronze, which is 4.5 meters, and the shear modulus for bronze, which is 35 times 10 to the power 9, plus the length for steel, which is 3.5 meters, and we divide by the shear modulus for steel, which times 10 to the power 9, and we compute to find the value for theta, and we need to have a value for angle, so we convert the value in terms of angle. So we have 180 degrees all over pi. So the value for theta, so 33,929 divided by 2.04 times 10 to the negative 5, and the summation for L over G, which is 4.5 divided by 35 times 10 to the power 9, plus 3.5 divided by 83 times 10 to the power 9, and we multiplied by 180 degrees over pi, and the value for theta, which is equivalent to 16.30, and it is in degree. So this is the angle of rotation.